Discussion 2.2, nuclear radiation and half-life. So in this discussion, we're going to talk about what radioactivity is and talk about the process of radioactive decay. We're going to characterize alpha, beta, and gamma radiation. We're going to talk about some uses for radioisotopes and use half-life information to determine the amount of a radioisotope remaining at a given time. Okay, so what is a radioisotope? So here we have our famous table of protons, electrons, and neutrons and mass number. So what I have here is two stable isotopes, nitrogen-14 and helium-4, and a whole bunch of unstable isotopes. So if I look at the ratio of protons to neutrons in the stable isotopes, I see that I have equal numbers of protons and neutrons in each. If I look at the unstable isotopes, I see I have a different number of protons and neutrons in each. So that is what makes a radioisotope an unstable isotope, is a difference in the number of protons and neutrons. So there's our definition. A radioisotope is an isotope with an unstable nucleus. It's unstable because it has different numbers of protons and neutrons in the nucleus. Now, a radioisotope can become stable by emitting a variety of particles. We call these emitted particles radiation. So here we have polonium-210. It's becoming more stable by spitting out something called an alpha particle. Carbon-14 can transmute into nitrogen-14 by spitting out something called a beta particle. So let's talk about this radiation. We have three types of radiation that we're responsible for knowing about: alpha particles, beta particles, and gamma rays. So alpha particles will have a symbol for helium. It will have the mass number of 4 and an atomic number of 2 like helium has. Now the composition of an alpha particle is actually just the nucleus of a helium atom. So it's the 2 protons and 2 neutrons of a helium atom without the 2 electrons. It's just the nucleus. That gives the alpha particle a charge of +2 for the 2 protons. As far as radiation goes, it's rather large, and alpha particles are so large they can just be stopped by air. So beta particles, their symbol is a lowercase e. They have a mass number of 0 and an atomic number of -1. Now their composition is electrons. That's why we give the beta particle the little e as a symbol. Now electrons, we know, have a charge of -1, and compared to alpha particles are going to be very small. Now beta particles can travel through air, but they can be stopped by something as thin as a piece of paper. And finally, gamma rays. We have the lowercase Greek letter gamma, which kind of looks like a little fish diving down, sort of, or a Y, with a mass number and an atomic number of 0. So the composition of gamma rays is pure energy. It's not really a particle at all. It does not have a charge associated with it, and it really does not have a size associated with it. So you can assume that gamma rays are super duper small. Now gamma rays can only be stopped by lead. Now you may remember, if you've ever had an x-ray, or when you go to the dentist to get the x-ray, they put that heavy vest on you. That's to prevent you from absorbing too much gamma radiation while they zap you with x-rays. Alright, so where in the atom does decay originate? Now we're talking about nuclear chemistry here. So these decay processes originate in the nucleus. Now, what is conserved in a nuclear reaction? Mass will always be conserved. What does that mean? That means that the mass will always stay the same during a reaction. If you have 10 units of mass before the reaction, you'll have a new substance that has 10 units of mass in the after the reaction. So here we have an isotope plutonium-240. Now, plutonium-240 is going to undergo alpha decay. That means it's going to spit out an alpha particle. Now, since an alpha particle has a mass of 4 and an atomic number of 2, the product that forms, uranium-236, will have a mass that is 4 units less than the mass of the original isotope. And it'll have an atomic number that is 2 units less than the original isotope, because we spit out 4 units of mass and 2 protons. Now, if you look at both of the products of this particular process and add them up, 4 plus 236 will give us a total mass of 240, and 92 plus 2 will give us a total atomic number of 94. So nothing changes from either side of the equation. All the masses are the same, all the atomic numbers are the same. So here are some equations for radioactive decay. Now, this was too much of a pain to fill in with the PowerPoint, so I'm going to do this with my document camera and my periodic table. So when we look at Part A. I have uranium-238. Now, in order to complete these equations, I need to have all the atomic numbers. So I'm going to get the atomic numbers from the periodic table. I look at uranium down here and I see it has an atomic number of 92. So I'll write in 92 down there to indicate that. Thorium on the periodic table is right near uranium and it has an atomic number of 90. So I'll write in the atomic number of 90. Now the whole idea here is that the mass and atomic number has to be equal on both sides. So on this side we have 3 different particles. All 3 particles have to add up to a mass of 238 and an atomic number of 92, since this is the only particle on this side of the equation. So I have thorium-234, and I have another particle that has a mass of 0. That means the mass of this missing particle must be 4, so that all 3 of them add up to 238. Now I know the particle with a mass of 4, if I look back at my table of the 3 types of radiation, the particle with a mass of 4 is an alpha particle. So I know that an alpha particle is being emitted. Now, since the alpha particle has a mass of 2, or an atomic number, of 2, these 2 atomic numbers combine to 92. That means this radiation must have an atomic number of 0, which means it's gamma. That's basically what we're doing here. We're just going to fill in the missing particles by determining what mass and atomic number they should have. So if I look at the atomic number for carbon-14, I see that carbon has an atomic number of 6 and nitrogen has an atomic number of 7. Now, we have 1 particle over here with a mass of 14, and we have 2 particles over here that will combine for a mass of 14. Since nitrogen-14 already has that mass, the mass of this particle must be 0. Now, since the atomic number over here is 6, the total atomic number over here needs to be 6. Now, nitrogen has an atomic number that's greater than 6, so the thing we need to add to 7 to make it 6 is -1. And the particle that has a mass of 0 and an atomic number of -1 is a beta particle. All right, I'll do one more, and then I want you guys to fill in all the rest on your own. So thorium is still 90, just like it was up here. Radium, if you look on the periodic table, is 88. That's an atomic number of 88. Now I see here the mass is 230. That means these 2 particles have to combine for a mass of 230. Since this particle is 226, this one has to have a mass of 4. Same thing with the atomic number. The atomic number over here is 90, which means it needs to be 90 over here. Since that particle has an atomic number of 88, this particle has to have an atomic number of 2, which makes it an alpha particle. All right, so pause the video and see if you can work out the rest on your own, and then I'll just go through them quickly. Okay, so polonium is right up here. It has an atomic number of 84. And we know that helium has an atomic number of 2. This is actually an alpha particle. So the total mass here is 218. Since the mass of helium is 4, the mass of this particle must be 214. And since the atomic number here is 84 and the atomic number of helium is 2, this must have an atomic number of 82. So to find the symbol, we have to find the element with an atomic number of 82. And we see that it's Pb, which is lead. So we'll write in the symbol for lead. Here we have our good pal thorium again. Thorium has an atomic number of 90, and Pa is protactinium, which is right there, has an atomic number of 91. So I'll write in 91 next to protactinium. So here we have 231 and 231, so the mass of this missing particle is 0. Here we have an atomic number of 90, and here we have an atomic number of 91, so we have to add -1 to that to make it 90, and this makes this a beta particle. Finally, zirconium-97. Zirconium is right here somewhere in the middle. Where are you? Where are you, zirconium? There you are. Atomic number of 40. So I'm going to write that in my equation right there. Now it's going to spit out a beta particle. Since the beta particle has no mass, the mass of this missing element will be 97. And since this is a beta particle, -1 plus 41 will make 40. And the element with an atomic number of 41 is niobium, which is Nb. And that is how you do the nuclear equations. This is something you can practice. Once you get the hang of it, you're going to find it's not that difficult at all. So some general rules for nuclear equations. The sum of the mass number on the left must be equal to the sum of all the mass numbers on the right. And the sum of the atomic numbers on the left have to be equal to the sum of the atomic numbers on the right. If you see the term alpha decay, it means that an alpha particle will be a product, which means that whatever, isotope is undergoing alpha decay will create a brand new element. So the mass number of an alpha particle is 4 and the atomic number is 2. If something is undergoing beta decay, that means it's going to spit out a beta particle and another element. The mass of the beta particle is 0 and the atomic number is -1. Finally, gamma decay means that a radioisotope is emitting gamma radiation, which means it will lose 0 mass and lose 0 atomic number. All right, so half-life. The question says, when does a sample of a radioisotope stop decaying? And the answer to that question technically is never. Now, we measure the rate of radioactive decay with something called half-life. Half-life is the amount of time it takes for 1/2 of an isotope to decay into another element. If the half-life for something is 10 minutes, every time 10 minutes goes by, the item will lose half of its mass. So we can determine half-life 2 ways, from an equation and from a graph. So let's first look at a graph. Now here we have on this graph activity counts per second on the y-axis. What that really means is the amount of substance remaining. And on the x-axis we have time. So the first thing we're going to need to do if we're going to determine half-life is to find the point on the y-axis that represents half of the item decayed. So at time equals 0, before decay starts, we have an amount left of 80. So the half-life must be at the point where 40, or half of 80, remains. Step 2, we're going to trace a line out to the curve and see where the intersection point on the curve falls on the x-axis. Wherever it falls on the x-axis, that's your half-life. So we'll trace out to the curve, trace down to the x-axis. We see it's just about between 4 and 8, so our half-life is approximately 6 days. Now here's the equation for half-life. The half-life is the total time duration of decay divided by the number of half-life cycles, which we can represent with arrows. So the time duration, again, is the amount of time the isotope has been decaying. We can determine the number of arrows by seeing how many half-life cycles it takes to decay to a certain mass. And you'll see what we're talking about in the next problem. But in most cases, these problems are going to require 2 steps. One step is going to be plugging the numbers into the equation. The other step is going to be figuring out how many half-life cycles or how many arrows we have to draw to make it fit the problem. So what does that mean? Well, let's take a look. So you have 3-gram sample of nitrogen-13. It takes 40 minutes for the sample to decay to 0.1875 grams. What is the half-life? So here's our equation. We're asked to calculate half-life, so we're going to need the time and the number of half-lives. Well, it tells us it's been decaying for 40 minutes, so we have the time. Now we just have to figure out how many half-lives. Well, we're not given the number of half-lives directly in the problem, but we are given a starting mass and a final mass. Now when we're drawing our arrows, 1 arrow will be equal to 1 half-life cycle. So let's start at 3 and see how many arrows it takes to get to 0.1875. Well, after 1 half-life, half of the sample will remain. So after 1 half-life, we'll have 1.5 grams left. After 2 half-lives, we'll have 0.75 grams. After 3 half-lives, we'll have 0.375. And after 4, we'll get to our 0.1875. So when we fill in the equation, our half-life, the time is 40 minutes, and it took 1, 2, 3, 4 half-lives to get there, so the half-life is 10 minutes. Now this one's a little bit simpler. It says how much of a 16 milligram sample of gallium will be left after 2 half-lives? Well, it's telling us how many arrows there are, and it's giving us a starting mass of the sample. So after 1 half-life, there'll be 8 milligrams left, and after two half-lives, there'll be 4 milligrams left. Really easy to solve that problem if you know what you're looking at when you read it. Try this one all on your own. It says, if the half-life of iodine-131 is 8.10 days, how long will it take a 50-gram sample to decay to 6.25 grams? So write down your equation, see what is missing from the equation, figure it out, and plug in the numbers and solve. All right, so here's our equation. Half-life is time over arrows. Right? So I'm given the half-life in this problem, right? And I'm asked to find the time duration. If I want to find the time duration, I have to determine how many half-lives it takes to go from 50 to 6.25. So let's find out. After 1 half-life, we'll have 25 grams remaining. After 2 half-lives, 12.5. After 3, we get to 16.25. So 3 is what we plug into the bottom of the equation. To solve, we're going to multiply 8.1 by 3, and we get that it's going to take 24.3 days for this to occur. Okay, so some uses of radioisotopes. Make sure you know at least one radioisotope and its use. So carbon-14 and uranium-238 are used for radiometric dating, or radiocarbon dating specifically if we're talking about carbon-14. Now, the way that works is we know how quickly a radioisotope will decay into a new element. So for carbon-14 is taken in the air that we breathe, in the carbon dioxide. So once an animal stops breathing, that carbon-14 will begin to decay. When the animal is discovered, we can look at the ratio of carbon-14 to carbon-12 in the bones or whatever, and we can determine how old it is. Now, because the half-life is 5,700 years, it only works for things that are about 50,000 years old, because after a while there will be so little carbon-14 left that it's too difficult to detect. Uranium-238 has a much longer half-life, 4.46 times 10 to the 9th years, or 4.5 billion years, basically has a half-life of the age of the Earth. So that is used to date much older things like rocks. All right, now, cobalt-60 is a beta emitter, meaning it undergoes beta decay, and it's used for disinfecting fruits. When a sample of cobalt-60 is placed near strawberries, the beta particles flying out can help to kill any microorganisms on the outside of the fruit, but it doesn't leave any nastiness behind like pesticides do. Phosphorus-32 has a number of applications, but one of them is biological tracing. In the image here, we see the phosphorus-32 being input into a plant. As it travels through the plant, you can actually use a device called the Geiger counter, illustrated here, to actually see where the phosphorus-32 is going. In people, they can actually do this to determine where blockage is in people's arteries, because they can input the phosphorus-32 in your body and in your bloodstream, and they can watch it go all the way through your bloodstream. Wherever it gets caught up in your body, will tell them where blockage is. Now we can see the half-life of phosphorus-32 is 14.3 days. Now you don't necessarily want something that's emitting beta particles inside your body because it can damage your organs, but since it's got such a short half-life, it doesn't stay in our bodies for too long, and so it's not really dangerous to us. Americium-241 is an alpha emitter, and that is used in smoke detectors. I actually think this is really cool because you have a little radioisotope decaying, spitting out alpha particles in your house right now. And the way a smoke detector works is there's a constant stream of alpha particles coming out of that americium-241 at a constant rate. And there's a detector in the smoke detector, and as long as the alpha particles are hitting the detector, the device is happy. It's only when smoke gets into the smoke detector, it blocks the alpha particles from hitting the detector, and that makes the thing freak out and make a bunch of noise. So I think that's actually pretty cool. Other medical uses for radioisotopes: iodine-131 with a half-life of 8 days is used to treat and diagnose thyroid conditions. They use iodine-131 because of its short half-life. But it's so radioactive that when people are given this treatment, they have to actually be quarantined because they're basically walking around being all radioactive. Iron-59 is used to determine iron metabolism and red blood cell count. Sodium-24 is used to test electrolyte levels in people. And cobalt-60, in addition to being used to disinfect fruit, is also used for cancer treatment. All right, so finally, I want you to practice determining the half-life for thorium-234 by looking at this graph. So pause the video and do that. All right, so the first step is to trace down to where half remains. So we started out at 100%, so 50% is half. So we'll trace a line from 50% out to the curve, see where that intersects the y-axis. It's right between 20 and 30, closer to 30, so I'll say it's approximately, the half-life is 28 days. All right, that's it for discussion 2.2 and unit 2. Make sure you watch these videos, bring any questions you have to class, and study hard for your test, which is going to be next week. All right, thanks for watching, and I'll see you in class.